Donc, bonjour à tous, bienvenue à cette session scientifique. Donc, nous accueillons aujourd'hui Arash Forodi, Manon Desclides et Simon Bioro pour des présentations. En fait, c'est des présentations qui vont durer à peu près entre 10 et 15 minutes avec 5 à 10 minutes de questions. Donc, nous allons commencer par Arash Forodi, qui est post-doctorant dans l'équipe imagerie, qui est arrivé au Lyric il n'y a pas très longtemps, et qui va nous parler de la caractérisation 3D du système de conduction cardiaque en utilisant la technique de transfert d'aimantation inhomogène.
Merci pour l'introduction. Bonjour à toutes et à tous. Moi, je suis Arash Forodi Gassamovodi. J'ai commencé en janvier. Je travaille avec Julie Magaz sur le projet Sinatra, caractérisation 3D de système de conduction cardiaque par le transfert d'aimantation inhomogène. Et aujourd'hui, je vais vous présenter ce projet. Je vais commencer par l'introduction du système de conduction cardiaque. Le rythme cardiaque est régulé par le CCS. Les composants principaux de CCS sont le NOSA, qui est le stimulateur naturel du cœur, et il est situé à l'oreillette droite avec un aspect blanchâtre à comparer de l'oreillette environnante. Et l'OSA est responsable pour régler le rythme cardiaque. Après, on a le NOAV qui joue un rôle fonctionnel en ralentissant le potentiel d'action par l'intermédiaire de jonction AV afin que les ventricules aient le temps pour se remplir de sang. Le faisceau de His qui est responsable pour conduire les impulsions électriques des oreillettes aux ventricules. Et les fibres de Purkinje qui permet la conduction de potentiel action dans les cavités ventriculaires. La perturbation de l'activité électrique du CCS peut provoquer l'arythmie cardiaque. On peut avoir la fibrillation auriculaire qui est le plus commun arythmie, et la fibrillation ventriculaire qui peut provoquer la mort subite, même chez les jeunes. Et il y a certaines études qui montrent que l'AFP peut être déclenchée par le système de Purkinje. Donc, notre objectif, c'est la cartographie 3D des fibres de Purkinje pour comprendre et caractériser l'arythmie cardiaque. Je vais commencer par les techniques déjà utilisées pour la cartographie du CCS. Je vais commencer par les techniques d'histologie, comme la procédure de trichrome Mason, qui nous permet de cibler la collagène et colorer la collagène en bleu, comme vous voyez ici, les noyaux en brun foncé ou noir et le tissu musculaire en rouge. Histologie est la technique gold standard de référence et c'est utilisé pour la validation des autres techniques avec une très haute résolution. Mais certains tissus et informations sont perdus quand on coupe les échantillons et il est très difficile à reconstruire en 3D. Nous avons quelques études pour l'imagerie de CCS avec IRM. Ici, je vais vous présenter en fait la première utilisation de la séquence GRO au champ 17,6 Tesla pour imagerie d'un corps de lapin pour visualiser les fibres Purkinje libres. Ici, vous voyez les flèches jaunes qui montrent les fibres libres. Et 2 ans plus tard, ils ont utilisé la même approche pour comparer les fibres de Purkinje d'un corps de lapin jaune et âgé. Et on peut voir ici la modification entre le réseau de Purkinje entre le lapin jaune et âgé. Mais la cartographie était faite que pour les fibres libres et ils ont utilisé un algorithme tensoriel pour suivre et segmenter les fibres. La technique DTI, Diffusion Tensor Imaging, était utilisée aussi pour construire un modèle de nœuds sinoatrial et pour déterminer l'orientation des myocardes dans un corps humain, comme vous voyez ici. Mais cette étude est faite avec un échantillon d'oreillette droite et on a une représentation 2D très limitée du corps. Les études plus intéressantes d'imagerie de CCS sont faites avec la technique de micro-CT. Ici, vous voyez la première représentation 3D du CCS entière dans un corps humain qui est basé sur les données micro-CT. Et on peut distinguer le nœud sino-atrial par une atténuation des rayons X inférieurs au tissu environnant. Un an plus tard, la même approche a été utilisée avec des agents de contraste pour l'imagerie d'un corps humain post-mortem avec une malformation septale auriculo-ventriculaire. Et on peut voir la disposition 3D du CCS et on peut identifier les voies lentes et rapides. Et on peut voir la modification entre le corps avec la malformation avec un corps normal. On a une résolution très haute dans l'ordre de dizaines de micromètres avec la technique micro-CT, mais les rayons X sont non massifs et normalement les échantillons ne peuvent pas être utilisés après l'application des agents de contraste. Donc ici, dans notre labo, on est intéressé par les techniques IRM 3D à très haute résolution pour visualiser le réseau. Et on doit avoir le contraste suffisant entre les fibres et le myocarde. Donc maintenant, on arrive à la technique de transfert d'aimantation, qui est une technique IRM pour l'imagerie des tissus avec une forte proportion de macromolécules. Ici, vous voyez la première étude avec MT pour imagerie 3D des fibres de Purkinje dans un corps de cochon qui a été publié par Maga et al. Et on peut voir les flèches noires qui montrent les fibres de Purkinje. Et on a un ratio MT plus élevé dans le tissu cardiaque à comparer des fibres. Et maintenant, on arrive à la technique de transfert d'aimantation inhomogène, Inhomogeneous Magnetization Transfer, ou IHMT, qui est un spin-off de technique MT avec une spécificité plus élevée pour les tissus myélinisés. Et donc, c'est utile pour étudier le système nerveux central et ses pathologies. Vous voyez les articles récents avec IHMT sur le cerveau et la moelle épinière. On peut voir les similarités entre la gaine de myéline entourant les axones avec la gaine de collagène entourant les fibres de Purkinje. Mais c'est quoi la technique de transfert d'aimantation inhomogène? On peut modéliser le tissu avec deux composants principaux. Le pool de l'eau libre, ici, et le pool macromoléculaire, avec les mouvements restreints. Et le collagène fait partie du pool macromoléculaire. On peut envoyer une impulsion de saturation RF simple, comme vous voyez ici, et saturer le pool macromoléculaire. Et on va avoir une réduction de l'aimantation Zeeman qui est contrebalancée par l'effet d'ordre dipolaire dans le pool macromoléculaire. Et ensuite, on a une réduction de signal de pool de l'eau libre à cause d'échanges avec le pool macromoléculaire. Et en soustrayant le M0 et M5, on peut arriver à signal MT, comme vous voyez ici. Ensuite, on peut appliquer une impulsion de saturation RF dual et on va découpler l'effet d'ordre dipolaire et l'aimantation Zeeman. Et en soustrayant le M single et M dual, on peut avoir le signal IHMT qui est basé sur le temps de relaxation dipolaire ou T1D. La preuve de concept de l'imagerie IHMT pour les fibres de Purkinje était présentée à la SFRMBM 2019 par Alio et al. On peut voir les fibres de Purkinje avec les flèches noires. Ils ont utilisé les différentes configurations de la séquence IHMT et ils ont montré qu'on peut avoir un contraste maximum de 2,4% entre la fibre et le muscle. Et donc, notre objectif dans ce projet est le développement et optimisation de la séquence IHMT pour l'imagerie 3D des fibres de Purkinje. Pour ce projet, on est en collaboration avec l'équipe IHMT à CRMBM à Marseille. Si vous voyez les PI et les deux postdocs, ils sont en train de développer un framework théorique et expérimental pour l'imagerie IHMT à courte T1D. Et on a transféré la séquence. Ici, vous voyez la séquence IHMT rare 2D. On a fait les premières expériences sur un fantôme d'après-shampoing et un fantôme O2P pour évaluer la séquence. Notre machine Bruker à 9,4 Tesla. Et on a les résultats qui conforment à ceux de Marseille, parce qu'à Marseille, ils ont la machine de 7T. Et après l'évaluation de la séquence marche bien, on va passer par l'imagerie ex vivo. On a récupéré les échantillons de la probie et de cochon, comme vous voyez ici avec les fibres, grâce à l'équipe physiopathologie. Merci l'équipe physiopathologie. Et on va envoyer certains échantillons à Marseille pour les expériences à 7T. Et on va garder le reste ici pour les expériences à 9,4. Et l'étape en cours, maintenant, on a commencé les manips sur les échantillons ex vivo avec le tissu et les fibres. On a les différents paramètres avec la séquence IHMT qu'on peut régler, comme la fréquence offset, le BNRMS, la forme et durée des impulsions. Et donc, on peut obtenir les différents contrastes basés sur le temps de relaxation dipolaire ou T1D. Et donc, nous allons tester les différents paramètres de séquence et étudier le contraste entre les fibres et le tissu. Merci pour votre attention.
Merci Arash pour ta présentation. Est-ce que vous avez des questions?
Le trichrome de Masson, pourquoi il colore les fibres de Purkinje? Qu'est-ce qu'il colore exactement?
Avec histologie?
Oui, pourquoi les fibres de Purkinje deviennent bleues?
En fait, avec une forte proportion de collagène. Comme on voit ici, en fait, ça c'était cette image que j'ai montrée, c'était pas avec, c'était pas sur les fibres. Je pense que ça c'est le nœud sinoatrial. Oui, ici, on a une forte proportion de collagène et c'est coloré en bleu. Parce qu'on cible les collagènes, le contenant de collagène. Et dans les fibres de Purkinje, on a aussi une forte proportion de collagène. Ça dépend du type de collagène, mais type 1 et type 3 dans les fibres de Purkinje.
Ça marche, ouais. Ouais, en gros, c'est juste le gain de collagène qui est coloré par le Masson trichrome. J'avais une question juste pour mieux visualiser comment vous arrivez à voir les macromolécules avec ces séquences NT. C'est quoi, quelles propriétés des macromolécules se rendent plus visibles, si tu veux? C'est la composition, le fait qu'ils ont les chaînes longues, la configuration.
Ah oui, donc, ok, je vais essayer d'expliquer un peu plus ici, parce que, ok, non, pas ici, avec ce diapo, oui. En fait, la technique de transfert d'alimentation en homogène, c'est récent, ça a commencé en 2015, mais transfert d'alimentation, ça a commencé en les années 90, je pense. Mais en fait, avec le transfert d'alimentation, parce que en fait, ça c'est un modèle simple. On peut modéliser avec le tissu avec un pool macromoléculaire et on peut avoir les différents types de macromolécules. Par exemple, on va avoir, comme c'est utilisé, la myéline ou même la collagène. Et donc, dans ce pool, en fait, quand on envoie l'impulsion de saturation, on va saturer ce pool. Et comme vous voyez ici, On a saturé, par exemple, on peut cibler soit la fréquence offset positive ou négative dans chaque côté. Et il y a un peu en homogénéité pour ce pool. Mais quand on fait la saturation de ce pool, après, on a l'échange entre le signal de l'eau libre et le pool macromolécule. Donc, on a une réduction du signal de l'eau libre. Je ne sais pas si j'ai répondu à votre question.
Est-ce que dans tout ce pool macromolécule, est-ce qu'il y a une sélectivité?
Ok, oui. Donc, oui, c'est une bonne question. Et en fait, donc par exemple, quand on envoie l'impulsion de RF pour saturation, ça dépend de quelle fréquence offset on va utiliser. Par exemple, dans le cerveau, pour la myéline, on a utilisé normalement on a 7 kHz ou 8 kHz. Mais oui, c'est une bonne question et on ne sait pas exactement, par exemple, pour chaque macromolécule, si on parle de la myéline ou de la collagène, c'est exactement dans quelle fréquence offset. Et donc, c'est pour ça que aussi dans notre projet, on doit balayer les différentes fréquences d'offset, on doit essayer les différentes fréquences offset. Et par exemple, pour le collagène, avec le transfert d'alimentation, moi, j'ai vu des articles qui ont utilisé en fait, ils ont le signal plus élevé à 1,5 kHz ou même moins parfois, par exemple 1,5, ça dépend des autres paramètres de la séquence aussi. Mais 1,5, 3, mais par exemple pour la myéline, je pense que c'est plus élevé la fréquence offset.
Et pardon, juste une dernière question. Est-ce que vous avez remarqué un signal au niveau d'endothélium ou épithélium? Et je parle surtout d'endothélium parce qu'il y a toutes les parties de réseau distal de Purkinje, ils sont situés là. Je me pose des questions, ils n'ont pas les mêmes dimensions que les fibres libres, qui sont typiquement assez gros. Et peut-être vous avez un signal intermédiaire au niveau d'endothélium, par exemple. Ouais.
Arash, j'ai juste une petite question qui suit, c'est en partie une question que j'avais déjà posée à Julie, je pense, mais pour suivre ce que disait Eric, donc là vous travaillez sur des tissus sains, donc le rôle du système de conduction comme pourvoyeur d'arythmie, c'est souvent dans des tissus pathologiques, avec un remodelage tissulaire, avec de la fibrose. Donc là, il va y avoir une question, si vous vous focalisez sur le collagène, comment vous allez arriver à distinguer le collagène qui va entourer les fibres de Purkinje du myocarde remodelé. Et donc, du coup, quand vous allez faire ces essais de balayer la fréquence pour essayer de faire ressortir d'autres pôles macromoléculaires, je me pose toujours la question, est-ce que le glycogène n'est pas un pôle macromoléculaire intéressant vu qu'il y a d'énormes stores de glycogène dans les fibres de Purkinje? Et est-ce que c'est quelque chose?
Oui, ça c'est une bonne question. En fait, il y a beaucoup de... Il y a beaucoup de inconnus dans ce projet. Oui, en fait, je pense que oui, pour la prochaine étape, on va essayer de cibler les fibres libres et dans le tissu sain. Mais après, par exemple, on se posait la question aussi pour la gaine de collagène. On a essayé sans succès avec collagénase d'enlever en fait le collagène, de voir l'effet. Mais après, par exemple, ça n'a pas marché parce qu'en fait, on a la fibre qui collapse aussi. Et donc, ça, c'est une bonne question. Et peut-être, je pense que la première étape, si on peut optimiser le contraste pour le fibre libre dans le tissu sain, parce que pour l'instant, il y a beaucoup de paramètres qu'on ne sait pas comment régler pour avoir un bon contraste. Et dans la prochaine étape, peut-être on peut faire l'imagerie aussi pour le tissu pathologique, par exemple, et on peut voir la différence.
Comme tu mentionnais l'offset, la fréquence d'offset que vous allez varier, je me posais la question, est-ce que du coup vous savez à quoi ça va correspondre ou pas?
Et c'est pour ça qu'on ne peut pas vraiment faire les expériences. En fait, par exemple, on a essayé pour la première étape avec les fantômes, si on a un fantôme de collagène, mais ça c'est très difficile parce que, comme Julie a dit, en fait, le contraste, probablement, ça dépend de contenants comme collagène, mais aussi la structure. Donc, si on a un fantôme avec quel collagène et pas la structure, peut-être on n'a pas, par exemple, on a essayé avec des solutions de collagène, de poudre de collagène, on n'a pas de contraste avec IHMT. Donc.
Et l'après-shampoing, c'est pas du collagène, si? Mais du coup, vous avez une fréquence qui est bien calibrée pour ça.
On a juste validé ce qu'ils nous ont envoyé comme ça, mais c'est pas le collagène.
Il n'y a pas d'autres questions?
Merci à vous. Merci Arash pour ta présentation. Nous allons passer maintenant à la deuxième présentation, celle de Simon Bioro, qui est doctorant dans une équipe INRIA, qui a commencé sa première année de thèse cette année et qui va nous parler du Numerical Model for Cardiac Ablation by Electroporation.
Sorry for the bar. It's okay. So I will first talk about a bit about myself and the context of my PhD thesis. Then I'll try to explain to you each term of the title of my PhD, and then we'll try to do some math because that's what I do in my day-to-day life. So this is me. I come from Caen, a really beautiful city located here. For those who don't know where it is, I stayed there until my baccalaureate. Then I moved in Paris to do some preparatory classes, and then I was admitted in an engineering school, ENSTA Paris, located near Paris. It's a general engineering school, but I specialized in applied mathematics and more specifically on analysis, modeling and simulation. Then 1 year ago, I started my end of studies internship here in Bordeaux, in INRIA and IMB, Institut Mathématique de Bordeaux, for those who know it, and where I worked on inverse problems on Maxwell equations. So it was more theoretical than what I do now. And I started in January 2023 my PhD, which is called the Numerical Model for Cardiac Ablation by Electroporation. Some context on my PhD. So it's funded half by INRIA and half by the French Federation of Cardiology through the Dielectric project. My supervisors are Michael Legeb from INRIA Carmen team, Annuel Collin from INRIA Monk team, and Claire Poignard from INRIA Monk team too. And this PhD also has some links with the ANR project MIR for VTAC, which tackles the modeling of irreversible electroporation for ventricular tachycardia. So there are collaborations, and so the Monk team is located in the IMB building, Institut Mathématique de Bordeaux, where I spend 3 days a week. The Carmen team is located in INRIA building, where I spend 1 day a week. And as you may know, the Carmen team also has some desks here at IHU Lyrics, where I spend 1 day a week every Friday for the Friday drinks. Okay, now I'll try to explain each term of the title of my PhD. So first, numerical model. So the goal of numerical models is to mathematically describe physical phenomena in order to then numerically simulate them. So it can help understanding how the physics works, and in fields like ours, it can help for doing kind of experiments numerically. Like we can test some parameters for the ablation process, and we can also try to predict short terms or long terms effects of the operations that we do on the tissues, on the heart. So, for instance, we know how to accurately describe the electrophysiological behavior of the heart, that is of the heart, through the bidomain equations that I write here. The next term is cardiac ablation. You certainly know better than me what all of this is, but I'll try to do my best. So the goal of cardiac ablation is to treat arrhythmias by blocking some electrical pathways in the heart, and for that we electrically isolate some regions by killing the cardiomyocytes of these regions. There are several methods to do that. The most frequently used is the radio frequency ablation. So the idea is to kill the cardiac cells with heat. Drawback of this is that there is no tissue selectivity, so it can damage other organs that are near the zone that we want to kill. A recent method in this field is the pulsed field ablation, or PFA, that kills the cardiac cells by electroporation, and it allows more tissue selectivity. So what is electroporation? Electroporation is a phenomenon that occurs when you apply an electric field on cells, and more specifically when you apply some high voltage and short duration pulses on the cells. So what happens when you do that? You can see two things happening. The first one is reversible electroporation. So some pores will appear on the membrane of the cell, but after some time it will go back to its initial state. So applications of that are for instance to put some things in the cells when the pores are open. So in oncology, for instance, you can do electrochemotherapy with that. Now, if you apply pulses with a higher voltage and shorter duration, you reach a point where you see irreversible electroporation. So now you still have some pores that are created on the membrane of the cell, but it as a result it kills the cell. As I understood, we do not really know what kills the cell. It could be by necrosis or by apoptosis. And this technique is used for many decades for tumor ablation, and more recently for cardiac ablation. And in this field, there are many open questions, such as how to know exactly what is the treated zone. So which cells did we effectively kill, and understand the impact of the thickness of the ventricle, for instance, if we work on the ventricle, and understand how the fibers position impact the resulting treated zone. Okay, so to sum up, the goal of my PhD is to find a mathematical numerical model that allows to simulate the electroporation phenomenon at the tissue scale in order to ease and to improve the cardiac ablation process with PFA. I hope it's clear for now. You will tell me after that. And now let's have fun. Let's do some math. So I want to present you some math that I can do in my day-to-day life. So what I will present you is the homogenization process. So what is it? Let's consider that we have a domain here, omega. So in a practice, it will be cardiac tissue, and this domain is composed of microscopic cells that we cannot really see at the macroscopic cell, like what we can see us as humans. So there is a microscopic scale and a macroscopic scale, and we have a model to simulate what happens at the cell scale, and we want to get a model at the tissue scale. Why? For numerical simulations, it's really less costly to have a macroscopic equation, and also to better understand what's happening. Sorry. To better understand what's happening in the macroscopic scale, we want to have the macroscopic equations. How to do that? There are many different methods. For instance, some of you may know the mixture theory. This is not what I do, so I will not talk about that. But what I do is homogenization. The idea is to introduce epsilon, which is the characteristic size of the cell divided by the characteristic size of the domain. So it's the ratio between the two scales. And we will make this quantity tends towards zero. So as if we were zooming out the microscopic scale. And we hope that it will get us the macroscopic equation. And as I pointed out here, it's the process that we use to get the classical bidomain equations that I presented you earlier to get the electrophysiological behavior of the heart. Usually, we can decompose it in three steps. The first one is to get the microscopic model. Then we introduce the epsilon, and we see how it appears in the equation, and then we make it tends towards zero to get the model at the tissue scale. And now how it is applied in what I do. So here is almost the same picture as before, but here we have a heart, which is the macroscopic scale, and the heart that is composed of cardiac cells, which is the microscopic scale. We have a model at the cell scale that describe how the electrical potential how it works for the electrical potentials inside the cells and outside the cells, and what are the exchanges on the cell membranes. So this is the last equation that describes the exchanges between the intracellular medium and the extracellular medium. As I said, okay, so the second step is to introduce epsilon. What I show you here is what is classically done to get the bidomain equations. So when we can consider the electrophysiological behavior of the heart, we get the first equation. And in my case, actually, some orders of magnitude are not the same, and also the time scale is not the same, so we don't get the same equation. As you can see, so I don't have pointer, but in the first equation we had epsilon beside the cm, and we don't have one in the second one, and we have another term in the second equation at the end, which represents the membrane conductivity. Okay. And now the first step is to make epsilon tends towards 0. So as I said, the first equation gives the bidomain equations, and the second one, what does it give? It's what I'm working on. So as I said, it's working in progress, because for now I did some big assumptions on some coefficients, so it's not done, but we have some preliminary results. Okay, we can't see everything, but what I can see for now is that we get equations of the same form as the bidomain ones, but we have a new term that is an advection term in the sense that it's proportional to the gradient of the electrical potential. So it's the electrical field. So it's proportional to the electrical field, and it's good. We think that this is a good thing, because there are already some proposed models in the context of tumor ablation. These models are phenomenological, so they are not from a process as I showed you. And when we choose to put some advection terms like this in these models, we can accurately find what we see in the real experiments. So it's like a trail that it's a good thing to have an advection term in the resulting model. And I'm still working on this, and can talk about that if you want more details. This is the end of my presentation.
Thank you very much, Simon. Do you have any questions?
Thank you. I have a question about your last slide. So the way you introduce electroporation, so this is a scalar term in transmembrane potential. So I'm not sure I understand correctly this last term that represents electroporation.
Okay.
So
yeah.
UI minus UE, this is the transmembrane potential.
Exactly.
And SM is just a multiplicative factor?
Yeah, okay. So this term is usually in the ion term, and but we assume that in electroporation, this term will have a bigger impact than the other terms in the ion, which represents the ionic currents occurring at the membrane scale. Sorry. So we get it out of this term, and for now the conductivity is supposed constant. But the next step is actually to assume that it's nonlinear and that it acts as a sigmoid in function of the transmembrane potential.
Okay. Does this term take the geometry of the membrane into account, the geometry of the cell? Because the membrane, the cell is not just a little brick; it has also T-tubules, which makes you have a lot of geometrical information that is important to take into account how your pulse will actually polarize your cell membrane. So I was wondering if this is something at this stage you include, or it's just a very general term that is lumped across the whole cell.
You mean in the SM?
Yes, well, in the electroporation term, yes.
Okay, because the thing, I'm not sure that it's the good answer to a question. You will tell me. But in the resulting equations, there are some coefficients that actually depend on what we call the cell problem, and so it's like quantities that solve a problem on the normalized cell. And so here is it's in these terms that we can take into account the geometry of the cell, if it's asymmetric or it's the geometry of the cell.
Okay, thank you.
Right. Maybe one question. Thank you for the presentation. We do know that there is a dynamical effect of the impulse when you do electroporation, because depending on the shape of the impulse, it can change a lot the effect you have on the cell. So maybe it means that I don't see how you will treat this dynamical effect of the pulse, because if SM is a static term, I don't know how you, but do you have a comment on how you will treat this dynamical effect of the pulse?
For now, the dynamical effect is only taken into account through the CM time derivative. It's a dynamical term, but as you said, if when we will take as SM not constant, we could have a game between the CM dynamical term and this nonlinear term, and we could have maybe it will be enough.
So according to your model, there is no additional capacitance involved in the circuit that can change the dynamical effects. It's only the capacitance of the cell membrane that will act for this dynamical effects. Okay.
And yeah, for this presentation and still in my work, I didn't consider some precise ionic model, but yeah, I think the time can be also considered in the ionic model that we choose. So in the term ion, maybe we could see some time effects.
About the conductivity models, actually, so Simon didn't write it because he's doing the theory with a constant SM right now. But we have already derived some dynamical models for this law on SM, which depends also directly on the transmembrane voltage. And since it's much larger than usual during application of the impulses, it's also already oriented in the direction of the field you impose with the electrodes. So actually, the geometry is found by much larger differences towards the poles of the cell, well, in the direction of the field. So, well, there will be two poles. Well, it will be more electroporated at two poles, the cells, than on the side. So. And of course, the shape of the cell orients also itself a bit the electric field in the case, so the geometry is taken into account by that.
You assume a constant conductivity, and you mentioned that you want to do so maybe be a sigmoid later, but in reality, the conductivity is very varies a lot in time. And it's also different for different ion species, which are there in different concentrations. So it's a huge simplification. Why don't you just use the bidomain model? Why do you have to use this simplification? Why don't you just use the bidomain model to simulate electroporation? Maybe you made the point, but I didn't understand it. But can you explain that?
Yes. The thing is that the bidomain model was found with assumptions of some coefficients, orders of magnitude, and on the time scale that are not true anymore when we consider the electroporation phenomenon. And that's why I have some terms that are not the same, but I mean, if in the bidomain model, yeah, okay. I think it's an assumption we made that we only get the SM part out of the ion, but yeah, maybe as I understand that you said, we could get some other terms out, but I don't know if it could be useful. Because
my question is, why don't you just keep everything in and use a bigger computer?
because I don't know. Because
well, in this stage of your PhD, you can say because the boss told you to.
Okay. Because the boss told me. No.
When you're defending your thesis, I want a real answer.
Okay. I will prepare one. Still have 2 years.
Thank you very much. Maintenant, nous accueillons Manon Desclides, qui est doctorante en équipe imagerie et qui va nous parler du Real-Time Automatic Temperature Regulation during in vivo MRI Guided Laser-Induced Thermotherapy.
Okay, hello everybody. So I will present you some of the results I had during my PhD that I am doing with Bruno Quesson in the imaging team. So the results I will present you today are on the development of a real-time automatic temperature regulation algorithm for MRI-guided laser-induced thermal therapy. So what is laser interstitial thermal therapy? These are procedures, minimally invasive surgeries that are used for brain diseases treatment and also tumor treatment, and are performed by introducing a laser catheter into the targeted region. And the light is exploited for the to induce a temperature increase in the target region, whether at high temperature to hit the cells, and this is called ablation, and it leads the cell to death. And we can also hit at lower temperatures, and that is called mild hypothermia, to induce immune effects. So the main challenge for this kind of procedures is to be very precise when heating in terms of temperature in the tissue, because excessive temperatures can lead to to alteration of healthy structure around the tumor, and insufficient one can lead to incomplete treatment. And also the temperature is directly linked to the type of treatment we want to perform. So to answer this problem, we worked on the development of an automatic temperature regulation algorithm that adjusts the laser power at every moment to force the temperature in the tissue to follow the temperature the user defined before the procedure. And we do that under MRI to use the possibility of mapping the temperature under MRI. So to do that, we use this real-time MRI thermometry pipeline with a laser with a laser device of 976 nanometer of wavelength, and with a diffusing tip at the end. We inserted it in a swine leg muscle, and we placed the stack of slice for thermometry just around the probe tip at the end, and we made 8 slices every second under a 1.5 Tesla MRI, so a clinical one, with a single shot EPI sequence. And we were able to see the resulting images, thermometry images in real time and in 3D with the Certis Solution software. And in parallel, we implemented the regulation algorithm that was that allowed the real-time power control of the laser device. We implemented it in the Gadgetron, that is a reconstruction pipeline. And the input of this algorithm was the temperature profile the user wanted, and also the 3x3x3 voxel region of interest, where the tissue has to follow this profile. So the regulation algorithm is based on the PID controller equation. So a PID is for proportional, integral, and derivative terms. And the goal is to make this equation to tend to 0. That means that the error between the target temperature and the measured one it tends to 0. Sorry, and so to be more precise in terms of bioheating system, we use the bioheat transfer equation, and we made it to resemble to the PID equation, and then we were able to have the power term at each time. And as you can see, we need 2 coefficients. So one for the thermal absorption and one for the diffusivity. And so we needed to find those terms to be able to compute the power. So to do that, we before the procedure, we made one initial low power shot, so with a constant power. And by knowing all the parameter of the power, the laser power, we were able to fit the temperature increase at the maximum temperature point. And that allowed us to have the absorption coefficient. And by looking during the cooling period at the shape of the heat, we can fit it with 2D Gaussian. And the spread of the Gaussian allowed evolves linearly with the diffusivity, so we can get this coefficient also with this shot. Then we made 2 experiments. So the first one was a mild hyperthermia one, and we made 3 plateaus of 5, 10, and 15 degrees of increase during 300 seconds. And so the orange curve is the target profile. The blue one is the maximum temperature we found in the target region. In green, it's the mean in the region of interest. And in the red, it's the temperature on a point that is not non-heated, to check if the temperature is constant and looks normal. And so what we can see is that we have something that is quite good, because the mean of the error is really near 0, and also the root mean square error during the different plateaus does not goes more than 1 degree. And for a second experiment, we made only one plateau of 30 degrees of increase during 700 seconds. And so it's an example of ablation. And also we found that the mean was near zero, the mean of the error, and the root mean square error was of 1.3 degrees. And here I can show you some slices of at some times during the experiment, and you can see that the temperature is quite stable, and the thermal dose. So this is the impact on the cells. So we can consider that the pink one are dead, and so you can see that you have an increase of this area. So to conclude, we were able, to precisely control the maximum of in vivo temperature tissue for the mild hyperthermia and also ablation, and this was really stable during time, even for long treatment duration. And so it can really have an impact on those treatments, because we were able to do that under clinical MRI, and it allows to have a really precise thermal treatment. And so the next steps are to develop and adapt this algorithm to have multiple sources of laser with multiple fibers to have a lesion more larger, and thank you. And I wish you a nice weekend and a nice drink after.
Thank you very much, Manu. Questions?
Thank you for this talk. One question about the measurement of the temperature. So you did this in the MRI. So the temperature that the graph that we see, the blue line, is the one made by the MRI, or do you have an additional sensor that measures the real temperature?
No, it's all the curves you can see are from MRI measurement.
So the noise that we have, is it due to the measurement, the noise from the measurement, or is it due to the fact that because sometimes it's really difficult, you know this for sure, to adjust the PID, because PID there is multiple coefficients that you need to adjust, and you can either oscillate and have a very fast response, or have a slow response with no oscillation. So these oscillations, I was asking myself about this oscillation. Is it noise, or is it due to the response of your PID?
So it's both, because in red you can see the evolution of one voxel during time. So here it's only noise. You can see I didn't put the standard deviation of the noise, but I have to. And so in blue it's the maximum temperature we have at each time in the region of interest. So it's not always the same voxel. So you not just have the noise, you also have the error of the algorithm in it. I don't know if it answers your question, but yes, you have both in the blue curve.
Just had I've many questions, but just ask a couple of naive ones. Just for the results you showed, I'm not sure I understood the purple mark where I think it was a validation of the lesion that was formed.
Yes.
Can you just explain how you measured that, or where that comes from?
Yeah, it's like the integral of the temperature for one voxel. So it's a combination of duration and temperature. and when it goes above, yeah, when it goes above a threshold you choose, you can consider. So for us, it was a threshold for tumor cells, and we can consider in the literature we can consider that this threshold represents the cell death, and so we use this one. But there are many models to do that, and this one is yes a threshold, and it's quite like the integrative term of the temperature.
Just a second question. Why such a long wavelength is used? It's very much in the infrared. Presumably this gives you penetrance in the tissue and through the blood. But in terms of its destructive capacity, I would have thought a shorter wavelength would have been more destructive. So I don't know if you have that explanation.
If you look at the graph where you plot the absorption of the wavelengths, there is I'm sorry for my English. You at this wavelength, the hemoglobin and the water have a minimum, and we use this wavelength to have to have the light that goes the more deep in the tissue, and that's why for cutting lasers, you have really longer wavelengths, like CO2 lasers. It's where it's the most absorbed, because you have to cut, and so you need an absorption, and you don't want this spread of light in the tissue. So we really want this spread of light in the tissue to have a maximum, to have the largest area heated.
Merci beaucoup, Manon. Merci Arash, merci Simon pour vos présentations. Maintenant, nous sommes tous invités à aller prendre un verre au Friday Drinks.